नमस्कार दोस्तों, वेलकम टू गेट वाला। मैं हूं सतीश कुमार द्रिशेट्टी, फैकल्टी ऑफ ऑप्टिकल इंस्ट्रूमेंटेशन। मैं आप सब लोग को स्वागत कर रहा हूं। लास्ट क्लास में हमने ऑप्टिकल इंस्ट्रूमेंटेशन में बेहतरीन एलईडी का क्वेश्चंस डिस्कस किया था। सो आज हम चालू करेंगे न्यू टॉपिक्स ऑप्टिकल इंस्ट्रूमेंटेशन में, दैट इज ऑप्टिकल फाइबर। सो टुडेज टॉपिक आई एम गोइंग टू कवर द ऑप्टिकल फाइबर एंड इसके ऊपर जो भी क्वेश्चंस आया वो भी सॉल्व करेंगे। सो जितने लोग लाइव में हैं मुझे एक बार हाई मैसेज डाल दिए, कितने लोग लाइव में हैं। सो ऑप्टिकल फाइबर्स के ऊपर जो जो क्वेश्चन है हम करके करके जाएंगे। Okay, first of all, we'll try to complete optical fibers, then we'll go for the interferometry. Okay, so interferometry also we are going to discuss today. Okay, so before going for that, so let us see some of the questions recently asked. So because optical में बहुत सारा कम weightage है, लेकिन जो भी questions आ रहे हैं repeated topic से आ रहे हैं, so उसका miss मत करना है। Okay, so we should not miss those topics. So let us see what are the questions asked in the recent times. Okay, some of the important questions also will discuss, क्योंकि ऑडियो वीडियो सब कुछ क्लियर है। मुझे एक बार वॉइस कंफर्मेशन कर दीजिए बेटा, ऑडियो वीडियो सब कुछ क्लियर या नहीं। सो फटाफट जाएंगे। सुबह सुबह अच्छा चाय पी के आपका प्रिपरेशन कैसा हो रहा है मुझे पता है। एवरीबडी स्ट्रगलिंग, एवरीबडी इज इन ए सिचुएशन ऑफ टेंशन फॉर द एग्जाम। सो आई हैव कलेक्टेड सम ऑफ द गुड क्वेश्चंस, सो ट्राई टू आंसर दिस क्वेश्चन। दिस इज अ गेट 2025 का क्वेश्चन। मेक इट फास्ट माय डियर। सेवन मेंबर्स आर वाचिंग द सेशन, सो मुझे कंफर्मेशन कर दीजिए बेटा। चलो ट्राई टू आंसर दिस क्वेश्चन, मेक इट फास्ट। Chalo, what is the answer for this? Chalo. It's a very simple question. This is light emitting diode emits light when it's dash biased. A photodiode provides maximum sensitivity light when it is dash biased. So always remember, LED is an optical source. LED is an optical source. Okay, so this is a photodiode. So what LED will do? LED takes the input current. It is an optical source. It is an input I bias. It gives I bias. It generates the light. But whereas this is different. Photodiode takes light and it generates the current. So this is an optical source. This is an optical detector. Optical detector. So try to understand that. So LED is connected in forward bias. LED connected in forward bias. Whereas photodiode is a PN junction diode. It is connected in the reverse bias. Reverse bias. So if you see now, so this is the I bias, which is going like this, and this is our P optical. Okay, so whereas this one, light is falling and the photocurrent is generated here. Okay, so LED is forward bias, this is reverse bias. LED conducts in forward bias. This is forward bias. This is reverse bias. Okay, so let us go for the next question. See this question also. Simple questions, but don't miss them. The correct bias conditions of LED. LED is forward bias. Remember this. LED is forward bias. Next, photodiode. Photodiode is reverse bias. Next, Zener diode. Zener diode is also reverse bias. So if you see the application, this is. So if you see the application, these are optical source. So this is the optical detector. This is the voltage regulator. Voltage regulator. So now write answers. LED, photodiode and Zener diode. LED works in forward bias, photodiode reverse bias. This is also reverse bias. So option A is the right answer. Answer this question. GATE 2017 का सवाल है. The band gap in electron volts of a semiconductor material required to construct a LED that emits a peak power at the wavelength of 620 nanometers. See the point here is, so these are the two energy levels. So this energy level 1, this energy level 2. Electrons are waiting here. आपने bias current दे रहे इसको. So when you give the bias current, the electrons are moving up. So when electrons moving here, holes are formed here. So now this 10 to the power minus 8 seconds के बाद, they are falling down. So photons are released. So this energy of the photon is equal to E2 minus E1, energy gap, which is nothing but energy gap in electron. Energy of the photon is equal to E2 minus E1, which is nothing but E2 minus E1. Okay. So energy of the photon is nothing but energy gap, which is given as hc by lambda. So what is the h? That is 4.14 into 10 to the power minus 15 electron volt a second. The c is the velocity of the light, that is given as, so you can solve that, minus 15, this is 2.998, approximately you can take 3 into 10 power 8, the whole divided by lambda, that is 620 nanometer, 620 into 10 power minus 9. So if you simplify, how much you are going to get? 4.14 into 3 divided by 620. So you are going to get into 10 power minus 7 plus 9, 2. So you are getting 2.003 electron volts. So the right answer is this, 2.003 electron volts. So make it fast. चलो, so please don't forget this pre-rankers club program for GATE ESC aspirant. Last chance, don't miss. Okay, so you can use this. Chalo, now we'll go for some of the beautiful questions, some of the concepts on optical fiber. Some of the concepts on optical fiber. Let us go for optical fiber. What happens on optical fiber? Let us go through it, and after that we'll go for interference also. So this is our ray theory. So if you see the ray theory, so whenever light having a refractive index of light is given by this formula. Please make a note of this refractive index of a formula. You see this? Yeah. So diffractive index of a medium depends upon the density. So as the density is increasing, refractive index also increasing. For example, refractive index of air is 1, refractive index of water is 1.33, refractive index of glass is 1.5. Good morning, Guruji. Yeah. So refractive index of medium is given by velocity of light in space to velocity of light in the medium. So velocity of the light in space is 3 into 10 power 8 meter per second. So if you take the velocity of the light in the air, so that is 3 into 10 power 8 meter per second, and 1.3, so that is 3 by refractive index of the medium. Okay, so velocity of the light in the water 2.3 into 10 power 8 meter per second. So C by V, so this is 2 into 10 power 8 meter per second. So these all are the different refractive velocities. Okay, so as the refractive index is increasing, the velocity is decreasing. So the continuous relation here is inversely proportional relationship. So next, so mu is inversely proportional to velocity. So I can write mu1 by mu2 is equal to v2 by v1. So mu1 to 2 is called as relative refractive index of medium 1 with respect to medium 2. Medium 1 with respect to medium 2. So mu2 1 is equal to relative refractive index of medium 2 with respect to medium 1. So that is v1 by v2. So mu1 to 2 means mu1 by mu2, that is v2 by v1. So mu2 to 1 is equal to mu2 by mu1 is equal to mu1. So this is what relative refractive index. So these are also formulas. Please make a note of these formulas. These all are useful for you. So next comes refraction. Law of reflection. So law of reflection tells that angle of incidence is equal to angle of reflection. So this is what law of reflection, my dear. This is what law of reflection. Okay, so take care. Yes. Business hacks. Okay, note down. Now I'm going for the refraction. So this is a refraction. So what is the law of refraction? If you see, so this is the theta I, so this is the theta R. So this is the angle of incidence, this is the angle of refraction, theta I and theta R. So this is the air and this is the glass. So the refractive index is less because air density is less. Air density is less, so refractive index is less. Glass density is more, refractive index is more. Okay, so when the light enters from the, so whenever is the density is less, उसको हम क्या बोल सकते हैं, रेयर मीडियम बोल सकते हैं. Whenever density is more, हम क्या बोल सकते हैं, डेंसर मीडियम बोल सकते हैं. अगर लाइट रेयर टू डेंसर जाए तो क्या होगा, ये रे इज बेंट टुवर्ड्स दिस नॉर्मल. सपोज अगर रे इज एंटरिंग फ्रॉम डेंसर टू रेयर मीडियम, इट गोस अवे फ्रॉम द नॉर्मल. ओके, सो note 1. When light enters from rarer medium to denser medium, it bends towards the normal. Note 2. When light enters from denser to rarer medium, it goes away from the normal. It goes away from the normal. Okay, so see here. So these are the formulas. Snell's law. Please make a note of this Snell's law. Angle of incidence, as angle of incidence is increasing, angle of refraction also increases. As angle of incidence increasing, angle of refraction also increases. So theta I and theta r, if we check, as a theta I increases, theta r also increases. For a particular angle of incidence, the theta r will be 90 degrees. So for a particular angle of incidence, theta r will be 90 degrees. So if you see that theta r, so sin theta I by sin theta r is equal to sin 90, this one, mu 2 by mu 1. So if I apply the Snell's law, sin theta by sin theta is equal to mu 2 by mu 1. So for a particular angle of incidence called as critical angle, so this theta is 90. So theta c is equal to sin inverse of mu 2 by mu 1. So where theta c is called as critical angle. So what is this theta c? This theta is c is treated as critical angle. It is the angle of incidence like this. Sure. Increasing, theta r also increases. So this is the theta I. So when theta is greater than theta c, for a particular angle of incidence, the ray will be refracting back. So that is what we call as total internal reflection. That angle of incidence at which the ray comes back, that is called as total internal reflection. So conditions for total internal reflection, if we see two conditions, the light has to enter from denser to rarer medium, then only it will go away from the normal. So first condition is light has to enter from denser to rarer only. Denser to rarer only. So if this is theta I, if theta I is greater than theta c, then this will reflect back. So this is a working principle of optical fiber जो आजकल हमने optical fiber communication में use कर रहे. So this is the mechanism they are using. So if we go for this optical fiber, so let us see the optical fiber working. So how the optical fiber works. Optical fiber is a channel for light which acts like a waveguide, and transfers the information in the form of light by using the concept of total internal reflection. So how the optical fiber look like? So if you see the optical fiber diagram, so optical fiber is having a core, this is the core, and this is the cladding. Okay, so now if you see this is a fiber axis, this is a fiber axis. Okay, so now if you see this is our The core, this is a cladding. So this is our mu1, this is our mu2, this is our mu naught. Air is the medium. Now this is a glass. This is a core 1.5, this is a 1.45, this is a 1. Mu naught is refractive index of air. Mu1 is refractive index of core. Mu2 is refractive index of clad. Okay, so when the light incidents now like this at this particular point, so now if you check this particular situation here, so this is what we call as acceptance angle. So then it enters. Why? Because light is now entering from the air to the core, so it bends here. It bends here. So this is the angle of refraction, theta r. Now it touches here. Okay. So now it makes perpendicular. So this one is 90 degrees. Okay. Like this. So this is the A, this is the B, this is C. Okay. So this is the propagation of light. How beautifully light travels like this. Check it. Understood? Now, what is going to happen there? Business hack, where are you from? Friend R3P, where are you from? Are you from instrumentation? Let me know. So now if you see, once it touches here, if suppose this angle of incidence is theta c, then the ray will be going like this. First condition. Okay. So if it is going like if it is touching like a critical angle, then this will be 90 degrees. So we know that. So let us take this is the interfacing point 1, this is interfacing point 2. So now if I derive the expressions, what I am going to get at interface 1, if you check at interface 1, if I check now, so this is the mu naught, this is a mu1, this is a mu2, right? So sine of theta a divided by sine of theta r is equal to sine of theta a by sine of theta r is equal to mu1 by mu naught. Mu1 by mu naught. So this refractive index is 1. So now I can write sine of into sine theta r. So this is our first expression. Next comes at interface 2. Interface 1 is what? Air core interface. Air core interface. Next comes interface 2. Next comes at interface 2. So if you check the interface 2, so what I can write, sine 90. So this is theta c, right? This particular angle is theta c. So I can make this angle as theta c. So sine theta c by sine 90 is equal to sine theta c by sine 90 is equal to mu 2 by mu 1. Mu 2 by mu 1. So this part I can take it as a critical angle. So sine theta c is equal to mu 2 by. Now if I take this particular triangle 1B2C, so this is 1, this is 2, this is C, theta R, theta C 90. This is theta R, this is theta C, this is 90. So theta R plus theta C plus 90 is 180. So theta R plus theta C is 90. So theta R is equal to 90 minus theta C. So now if I check this one, sine theta A is equal to mu 1 sine of theta R, right? So this I will write mu 1 sine 90 minus theta C. So this is the sine theta A. Sine theta A is equal to mu 1 cos theta C. Cos theta C is equal to square root of 1 minus sine square theta C. So if you write that mu 1 square root of 1 minus, this is mu 2 square minus mu 1 square. So I'm going to get as mu 1 square minus mu 2 square. So this is the acceptance angle, which is also called as numerical aperture. Numerical aperture is sine theta A, which is nothing but square root of mu 1 square minus mu square. Okay, make a note of these points. Done. Please note down. कर दिया. So now let us go for another category. So numerical aperture is sin theta A. Okay. Na is a light gathering capacity that is given as sin theta A, that is square root of mu1 square minus mu2 square. So sin theta A is square root of mu1 square minus mu2 square. mu1 square minus mu2 square. So this I will write it as square root of mu1 plus mu2 into mu1 minus mu2. This I will write like this also. This is mu1 plus mu2. If I take mu1 out, 1 minus mu2 by mu1. If I am taking this mu1 plus mu2, mu1 if I take, that is mu1 minus mu2 by mu1. So if I am taking this mu1 plus mu2 into mu1, so this is the delta. Okay, so where delta is mu1 minus mu2 by mu1, which is what we call as relative refractive index difference. So that is called the delta. You are expressing the difference as a relative term now. That's why it is called relative refractive index difference. So this is what we call as numerical aperture. And numerical aperture is also can be taken as sine of theta A. Okay. So now from all these formulas we can go for the questions. Fatafat. So let us go for the questions. So try to answer the questions. Some important questions we have discussed. Answer this question. Try to answer this question. Chalo. Take a time and answer the question. What can be the answer for this question? You see, a laser beam of 10 mm beam diameter. So this is 10 mm, means if you cut this is 5 mm. This is 5 mm. Okay, so this is 5 mm. This is the acceptance angle. This is acceptance angle. Okay, this is 5 mm. So refractive index of the core is mu1. Cladding is mu2. A laser beam of 10 mm diameter is focused on optical fiber using a thin biconvex lens as shown in the figure. The refractive index of the lens is 1.5. The refractive index of the core and cladding are given as mu1 by mu2. So that is mu1 is given. So this is the mu1. The mu1 is given as 1.55. Mu2 is given as 1.54 respectively. The minimum value of the focal length. So he's asking this focal length, this distance. This length, focal length, we call it as Fl. Minimum value of focal length of the lens to attain the maximum coupling to the fiber. So maximum coupling he is asking. So first of all, we can take this from use. You can find out the numerical aperture. Numerical aperture is square root of mu1 square minus mu2 square. So if you simplify, how much you are going to get? Kuldeep, answer batai yaar. So this is comes as 1.55 square minus 1.54 square. The square root of answer is coming around 0.1757. 0.1757. So if you see the numerical aperture is nothing but sine theta A. So sine theta A is given as 0.1757. This is given as 0.1757. Theta A is equal to sine inverse of 0.1757. Shift sine inverse of answer, that is coming as 10.124. 10.124. So now I need the tan theta A. So tan theta A is equal to, this is 5, this is the focal length. So now tan of answer is coming something 5 divided by answer 28. So focus length is coming as 28 centimeter. How many of you got the answer? He's asking in mm. So 28 mm, sorry, 28 mm. This is 5 mm na. So this is 5 mm. So this is 28 mm. 28. So the answer is 28 mm. So good quality questions, miss mat karna. Now let us go for some more questions. Answer this question. Please go through the question. Laser pulse is sent from the ground level to the bottom of a concrete water leg at a normal incidence. The tank is filled with water up to 2 meters below the ground level. The reflected pulse from the bottom of the tank travels back and hits the detector. The round trip time elapsed between sending the laser pulse, the pulse hitting the bottom of the tank, reflecting back and sensed by the detector is 100 nanoseconds. The depth of the tank from the ground level marked as an X meters is dash. It's a very good question actually. It's a very good question. So try to answer. So it is starting from the ground. From the ground it is going, this is the water. So it is coming like this and going back. A laser pulse is sent from the ground level to the bottom of a concrete water tank. So this ground, the water tank is at the underground. Water tank is at the underground. So from here I am sending a laser and it is coming back. The tank is filled with water up to 2 meters below the ground level. Up to 2 meters below the ground level. The reflected pulse from the bottom of the tank travels back and hits the detector. Here is a detector. The round trip time elapsed between the sending and laser pulse, the pulse hitting the bottom of the tank, reflecting back and sensed by detector is 100 nanoseconds total time. The depth of the tank from the ground level marked in X meters is dash. So please do it, answer it, try to get it the answer. So how to understand this question, how to do it? See here, let me take the diagram once. Let me take the diagram. So this is my diagram. This is my tank. Okay. So this is the ground level. This is the ground. Okay. Now this is 0 meters. This is 2. Beneath that there is a picture. Air is there. Up to this air is there. So here comes the air. Here comes the air here. So this is ground. This is air. 2 meters, and then comes the water. So this is 0. This is 2 meters, and this is X. X is actually, see the picture carefully. See the picture carefully. See the picture carefully. X is from this one. This total is X. This is, sorry, 2 to the ground is X is given. Okay. So this one is given as X. So this one is given as x. Okay, so it comes from the top of this, touches here and goes back to the detector. So what is the data given? See here, a laser pulse is sent from the ground level to the bottom of the concrete water tank. At the normal instant, the tank is filled with water up to 2 meters below the ground level. So this 2 meters below the ground level. So this height is 2 meters. So try to understand, this particular height is 2 meters. The reflected pulse from the bottom of the tank travels back and hits the detector. The round trip time elapsed between the sending the laser pulse, the pulse hitting the bottom of the tank, reflecting back and sensed by the detector is 100 nanoseconds. So refractive index of water is given. So refractive index of the water, we know refractive index of the air is 1. Refractive index of the water is given as 1.3 and the velocity of the light c is given as 3 into 10 power 8 meter per second. So first let us calculate the time. So velocity is equal to displacement by time. Okay na? So time can be taken as time is equal to displacement by velocity. So now here it travels a displacement of this and this, air displacement. So that will be how much velocity it will travel to and fro. If you check, it will come, when it comes here, it will like this. It will cover a displacement of 2 meters with a velocity of 3 into 10 power 8 meter per second down, and while going up also, when it comes up, this particular piece will cover with a velocity, displacement covers 2 into 10 power 8 meters. So t down and t up. So total t with air is what? 2 times of 2 by 3 into 10 power 8. So that will become as 4 by 3 into 10 power 8. Now T water, if you check, so this total is, suppose this is x, so this is what? X minus 2. So displacement by velocity in the water, velocity of the light in the water is what? C by mu. Am I right or not? Velocity of the light in the water is C by mu. Yes or not? X minus 2. So this total is x. So x minus 2 divided by velocity is what? C by mu, that is 3 into 10 power 8 divided by 1.33. It's given 1.33. So that will become as x minus 2 into 1.33 divided by 3 into 10 power 8. But it will be to and fro. If you compare, it should be multiplied with 2. Okay. So the total time will be 2 into 1.33, that is 2.66 by 3. Something is going to come here. 2 point, calculate karo. Kitna aa raha hai, check karo. 1.33 into 2 divided by 3.886. Okay, whatever it is. So I will write like this. This is 2.66 into x minus 2, the whole divided by 3 into 10 power 8. Done? Check. Now he has given the total time as how much? He has given 100 nanoseconds. So the total time is this na, T up and down water air and T air what? Air up and down. So total time, I can take the total time is equal to T air up and down, T of water up and down. So if you take the air up and down, how much that is? 4 by 3 into 10 power 8 plus this is 2.66 into x minus 2 divided by 3 into 10 power 8. And he has mentioned the total time as how much? 100 nanoseconds. Is given as 100 nanoseconds. So now if you simplify, x value you are going to get, that is 100 nanoseconds. The total time is 3 into 10 power 8, 4 plus 2.66 x minus 2 12 13 5.32. So 100 into 10 power minus 9, 3 into 10 power 8 is equal to 2.66x minus 4 minus 5.32. 1.32. Okay, so this will be 300 into 10 power minus 1, that becomes as 30. 30 is equal to 2.66x minus 1.32. 30 plus 1.32 is equal to 2.66x divided by x is coming as 11.77 exactly meters. Okay, so that was the answer. Anybody has done? Approximately 12. Okay, so that was a beautiful question. Try to answer this question on photodiode. Now see this. How to answer this question? In a pin photodiode, a pulse of light containing 8 into 10 power 12 incident photons at wavelength lambda 1.55 micrometers gives rise to an average of 4 into 10 power 2 electrons collected at the terminals of the device. The quantum efficiency is asking. So if you see the quantum efficiency of the photodiode, number of EHPs generated divided by number of photons incident into 100. We have percentage means into 100. So number of EHP generated is how much? 4 into 10 power 12. Number of photons incident is how much? 8 into 10 power 12. Okay. The quantum efficiency of the photodiode is asking, as a percentage is asking. So as a percentage of the photodiode is equal to into 100. So that will give as 50%. Right answer is 50%. Very simple, na? Very simple question. No need of worry about it. Chalo. Next. Photodiode is opposite to LED, right? Answer this question. A photodiode is made of a semiconductor with a band gap of 1.42 electron volts. So here the energy gap is given as 1.42 electron volts. Given that Planck's constant H is given 6.625 into 6 to 6 into 10 to the power of minus 34 joule second. Speed of light c is equal to 3 into 10 power 8 meter per second, and the cutoff wavelength is asking. So what is cutoff wavelength? See, the photodiode has to having the electrons like this. The photon is incident here. This is a photon. This photon makes this electron to rise up like this. So then these electrons will go here and then they fall down. That is secondary. Chalo. So now he is asking what should be the energy of the photon. This energy of the photon should be greater than, to lift up this energy gap is E2 minus, energy of the photon should be greater than that Eg, or Hc by lambda should be greater than Eg. That means lambda should be less than Hc by Eg. Okay, so how to do this problem now? So if you see this question, lambda should be less than or lambda should be less than Hc by Eg, but Eg is in electron volts, right? So Eg in electron volts, Eg value is given in electron volts as how much? He has given 1.42 electron volts, so you can write 1.42 electron volts here. So this I can take it as 1.42 electron volts, and H means 4.14 into 10 to the power of minus 15 electron volt second, and C is 3 into 10 power 8 meter per second. So now here second gets cancelled, electron volts get cancelled. So lambda cutoff is coming as how much? You can calculate by using the calc. So how much we are going to get? That is 4.14 into 3 divided by 1.42. So I am getting into 10 power minus 7. Oh, 874.647 nanometers. So cutoff means 875 nanometers we can take. Okay. The right answer for this question here is, the cutoff is asking, so answer will be 875 nanometers. Okay, va? Chalo. Can you answer this interesting question, anybody? See, this is some of the tricky questions. I give you some tricky questions here. Yeah. A car is moving co-linearly with a laser beam emitted by a transceiver. A laser pulse emitted t is equal to 0 seconds is received back by the transceiver 100 nanoseconds later after reflection from the car. A second pulse emitted t is equal to 0.1 seconds received back 90 seconds later. Given the speed of the light, the average speed of the car in this interval is dash. Very, very good question, physics oriented question. Question is related to laser. So try to answer this question. See, very, very good question. Try to understand. A car is moving collinearly. So this is the car moving collinearly with a laser beam emitted by a transceiver. A laser pulse emitted t is equal to 0 seconds is received back by the transceiver 100 nanoseconds later after reflection from the car. A second pulse emitted t is equal to 0.1 second is received back 90 nanoseconds later. A car is moving collinearly with a laser beam emitted by a transceiver. A laser pulse emitted t is equal to 0 seconds is received back by the transceiver 100 nanoseconds later after reflection from the car. That means what? If we assume the laser here, so this is a laser. So at t is equal to 0 seconds, it is emitted. Now what happens? It travels, it hits this 0 seconds received back by the transceiver 100 nanoseconds later. So 100 nanoseconds later. Within that 100 nanoseconds, this vehicle may be traveled somewhere. Okay. A second pulse emitted. Now that by the time the second pulse reaches here, so this is a laser. The second pulse emitted at t is equal to 0.1 second received back 90 seconds later. Received back 90 seconds later. So this is 90 nanoseconds later. Given the speed of the light is 3 into 10 power 8 meter per second. So how to understand this question? The average speed of the car, and within this 10 nanoseconds this could have traveled somewhere. Am I right or not? Yes or not? So the round trip time of the first nanopulse. So if you see the first pulse, the round trip time of first pulse is how much? And it is hitting the car and it is coming back. That is how much? So this is my car hitting and coming back. This is a laser, transmitter, receiver. Is how much? 100 nanoseconds. So 100 nanoseconds. So we can write the formula: velocity is equal to displacement by time. So time is equal to displacement by velocity. So the time is given as how much? 100 nanoseconds. It is a so how much velocity it is? 3 into 10 power 8, but travels a distance of how much? 2x, can I say? This distance, can I say 2x? Yes. So I can calculate the x is equal to t1 into velocity by 2. So that is given as 100 nanoseconds, 100 into 10 power minus 9, and velocity is light velocity 3 into 10 power 8 divided by 2. So it is coming as how much? 50 to 150, 150 to 50 to 50 into 3, 150, 150 into 10 power minus 1. So 15, it is coming around 15 meters. It is coming around 15 meters. This is one case. Is it clear? So this is a distance one. Same to same, second case. Same to same will repeat. The round trip time of the second pulse. I am just changing the letters. The round trip time of the second pulse. The round trip time of the second pulse is how much? Later, after reflection of the car, the second pulse emitted t is 0.1 seconds, received back 90 nanoseconds later. 90 nanoseconds. Whatever may be the time, it received by 90 nanoseconds. Okay. So it received by 90 nanoseconds. So this time is equal to 90 nanoseconds. So same to same we can use. In 90 nanoseconds, what is the distance travel? velocity is equal to distance by time. So time to t2 now, t2 is equal to x, this is, let us take x2, previously it was x1. Okay, ba? So now if you check, x2 is equal to t2 into v by 2. So this is 90 nanoseconds. So I can take it as 90 into 10 power minus 9. Velocity this. So how much I am going to get? So 45 into 3. I think it is coming around something 13.5. 13.5 now. So this is coming as 13.5. 13.5 meter. 45 into 3. 3 5 is 15, 3 13, 135, 10, 13.5 meters. So this is x2. This is x1. 15 meters and this is 13. So now question asked is what? See here. The average speed of the car in this interval is dash. So in this particular interval, how much is the speed is asking. So we can calculate the distance, how much covered. Yes or not? The average speed you have to calculate. First of all, we can calculate the distance now. Yes or not? So what is the time interval? Time interval is 0 seconds to 0.1 second. So within that distance, what is the average distance? Average distance is nothing but x2 minus x1 I can take, or x, whatever is the magnitude we can take. So average distance is 15 meters, this one, and this is, previously it was how much? 13.5. So t1 is equal to 0 second, t2 is equal to 0.1 second. Okay, x1 is equal to 15 meters, x2 is equal to 13.5 meters. So the average time covered is 0.1 second. The average distance covered is how much? 1.5 meters. So that is the speed, right? I can take that is the speed now. Yes or not? So average velocity of the car, is equal to average displacement velocity by average time. So that is 1.5 meters divided by 0.1 second. So 15 by 10. So I think 15 meter per second is the right answer. So answer kitna aa raha hai? 15 meter per second. So the right answer is 15 meter per second. So please remember this. Okay. Done. So answer this question now. Very, very good questions. These all are. Acha, he's asking per hour, right? In this previous problem, the previous problem, this is per 1 second. This is per 1 second, right? So in 1 second, it covers 15 meters. In 60 seconds, it covers 900 meters. In that means in 1 minute. 1 minute, it covers 900 meters. In 60 minutes, 16 into 900, 6 9 is 54,000 meters. అంటే 1 hour. 1 hour ki 54 kilometers. So speed will be 54 kilometers per hour, right? So options are given, right? That's why I'm asking. 54 kilometers per hour, moving away from the transceiver or moving towards the transceiver? Towards the transceiver. So why? Because the distance is decreasing, na? Distance is decreasing, so towards the transceiver. So the right answer is moving towards the transceiver. Option A is the right answer, 54 km per hour. Okay, so in the similar context, you try to answer this. Monochromatic light of wavelength 532 nanometers is used to measure the absorption coefficient of a material in a UV visible spectrophotometer. The measured light intensity after transmission through 1 centimeter thick sample of the material is 0.414 milliwatt per centimeter square. For a sample of thickness 2 centimeters, the measured light intensity is 0.186 milliwatt per centimeter square. The absorption coefficient of the material is dash. Think and answer this question. Question is related to UV visible spectrophotometer. So this is from the Beer-Lambert's law, a monochromatic light of wavelength. So see here, what I can do here, I can take a sample like this. This is a sample. So this is a sample thickness. So this is the breadth. So this is the intensity of the radiation incident. This is the II. This is the IT. Okay. A monochromatic light of wavelength lambda is given. 532 nanometers is used to measure the absorption coefficient of a material. Let us take the absorption coefficient is mu. UV visible spectrophotometer. So here comes the UV source and here comes the receiver. The measured light intensity after the transmission through 1 centimeter thick. So this is 1 centimeter thick. Sample of the material is 0.414 milliwatt per centimeter square. So here the available is how much after this? We don't know this II, but this is how much now in this case? Given as 176 centimeter is given as 0.414. Is 0.414 milliwatt per centimeter square. 0.414 milliwatt per centimeter square. For a sample of thickness 2 centimeters, for a sample of thickness 2 centimeters, so this sample of thickness 2 centimeters, so this is my transmitter and this is my receiver. So here comes Ii and this is I naught. So this is Ia and this is IT. So in this case, the IT available is how much? 0.186 milliwatt per centimeter square. 0.186 milliwatt per centimeter. The absorption coefficient mu is asking. The same case mu will be same. In both the cases mu will be same. So I can take the expression as what? We know the Beer-Lambert's law. So as per the Beer-Lambert's law statement, actually it's a Lambert's law statement, not Beer's law. So Lambert's law tells that IT is equal to II into e power minus mu into x, where is x is the thickness or the breadth. So first case law, how much we are having? 0.414 milliwatt per centimeter square. II is, we don't know. Thickness is, and how much thickness? That is B, 1 centimeter. This is 1 centimeter. Now the same to same, second time how much is coming? 0.186 milliwatt per centimeter square. 0.186 milliwatt per centimeter square, that is II into e power minus mu. This is how much? 2 centimeters. This is coming as 2 centimeters. So if you simplify this gets cancelled, this gets cancelled. So 0.414 divided by 0.186, that is coming as 2.2258 e power minus mu 1 centimeter plus 2. That becomes, if you apply ln 2.2258 minus mu into 3. Am I right? Any mistake we have done? Okay. 0.8 is coming minus 3. कितना आ रहा है? 0.8/3 आ रहा है ना? e power minus alpha कितना आ रहा है? Sorry, we can directly like this na. So this is e power minus 3 mu. So I can write like this. E power minus 3 mu is equal to this. Point, is it correct? Division 0.414 divided by 0.186. 2 point, okay, that's fine. 2.226. Sorry, I have done a mistake, right? It is a plus 2 mu. So 1 mu hoga na idi. This will become e power minus 1 mu. Simple mistake. E power minus 1 mu hoga. This is e power minus mu by e power minus 2 mu. E power minus by e minus 2. So a power m minus a power n minus plus 2 mu. So that will become e power minus mu. So that will become e power 1 mu. E power plus 1. So mu is equal to natural logarithm of this. So if you apply, I'm getting 0.800. Okay, so that is the absorption coefficient value. Okay, absorption coefficient value per centimeter. Very good question. 0.800 is the right answer. 0.800. Any doubts you can ask me. Very good question. Quality questions. Enough for today. Chalo. Enough for today.